So far we've been considering graphs where all the edges are the same. They're length 1 or they really don't have lengths at all. And we've talked about traversals of these graphs and what we can use these graphs to model. But for many situations where we want to use graphs to model the situation, there might be actually lengths or times or weights or costs associated with each edge. And we'll use these terms interchangeably: length, cost, time, and so on. For example, if you're building a graph represents a network of roads you're building, then the weight of an edge might be the cost to build the road corresponding to that edge. Or if the graph represents routers and hosts on the internet, then the weight of the edge or the number associated with an edge might be the time for data to traverse a link corresponding to that edge. Or if you're exploring a graph, the number on an edge might represent the length of the edge, so that might tell you how long it'll take you to explore from one node to the next on that edge. So you can see that it's very natural for graphs to have weights on the edges, and these are called weighted graphs. An example is given on the left here. So what's a weighted graph? So one thing I want to say before that, by default, unless I say so, we'll assume the weights are non-negative. But there will be particular cases where we will be concerned with negative weights, and we will point them out when they arise. A notation for weighted graphs. So we'll think of a weighted graph as a triple, G, which is a set V of vertices, the set E of edges as before, and a function W, which maps edges to their weights. So W of E is the weight of edge E. And again, this can be applied to directed graphs and to undirected graphs. And we will see two algorithms, two problems basically. One on weighted undirected graphs and another on weighted directed graphs. So let's look at the problem on weighted undirected graphs. The question we want to ask ourselves is, so given a graph with weights on the edges, how do we connect all the vertices with the least cost? I mean, again, cost could be length or time. So basically, we want to find a subset of the edges of the graph that creates one connected component of all the vertices. So all the vertices now lie in one connected component, connected by the subset, such that the sum of the weights of the edges in the subset is as small as possible. And for the moment, let's assume the weights are non-negative. So we know that trees are the minimal connected graph. So there's no reason to choose anything more than a tree, because we want to connect all the vertices, but we want to be as low cost as possible. If we add an edge if we choose a set of edges that have cycles in them, we're being wasteful, because we could get rid of one of the edges in the cycle and still have the graph be connected and potentially of lower weight. So we don't want cycles. So we want a tree, but we want a tree that connects all the vertices of the graph. Such a tree is called a spanning tree. A tree that spans over all the vertices of the graph is called a spanning tree. So the problem we have is the problem of finding a minimum spanning tree in a graph, or the MST in a graph. And we will give two algorithms for this problem and then argue that they are correct in the next segment. Next segment. So the first algorithm is Kruskal's algorithm. So here is an example graph, and Kruskal's algorithm is actually an example of a greedy algorithm. What it does is it makes a series of decisions at each point, choosing what looks like the best possibility at that point, and in the end it'll turn out it's producing the best tree. And again, this will be an algorithm that's complicated enough that without a proof of correctness, you really don't know if this algorithm is actually producing the minimum spanning tree or not. So let's describe Kruskal's algorithm. What it does is it sorts the edges in increasing order of weight. And if there are ties, it breaks ties arbitrarily. So say non-decreasing order of weights, E1 is the lightest edge and EM is the heaviest edge. And then it computes a solution set S. So it's going to be a set of edges S that it's going to compute. Initially, the solution set S is empty. Then it goes through the edges in the sorted order. And for each edge, it says, does adding this edge EI to the solution set S cause a cycle? If it doesn't cause a cycle, it adds edge EI to the set S. If it does cause a cycle, it just ignores edge EI and goes on to the next edge. So it adds an edge to the set S if and only if the addition does not cause a cycle. So that's Kruskal's algorithm in its entirety. Let's see how it would work in this graph. You can see clearly the lowest weight edge is BA. That's got to be the number 1 edge that it considers. The number 2 edge is probably going to be it has to be the edge DA. And as for the other number, the third edge could be any of the ones which have weight 2, and there are several options. We'll see how this algorithm goes. So it first considers the edge BA, and clearly we don't have any other edges at the moment, so the addition of BA does not cause any cycles. And so it adds BA to our solution set S. Then it considers DA, and again, the addition of DA does not cause any cycles, as you can see. Right now we only have 2 edges and they don't cause a cycle. So DA is added. So then maybe it considers AE and realizes adding AE does not cause a cycle either and adds AE. At this point, maybe it considers the edge DE. This is the edge DE right here. And that might be, because it's got to consider some weight 2 edge, and it might be the edge DE. But it realizes that the addition of the edge DE actually causes a cycle with the other 2 edges that have been chosen. And so it just ignores it drops the edge DE, does not add it to the set S. And it continues in this manner. It considers the edge FG, which is also weight 2, doesn't cause a cycle, adds it. Considers the edge FH, doesn't cause a cycle, adds it. And maybe it considers GH now. And of course, if you add GH, that would cause a cycle, so it does not add the edge GH either. Onward to weight 4 edges, so it adds the edge AF, and that doesn't cause a cycle, and the edge CF doesn't cause a cycle either. At this point, it actually has a spanning tree, but you could imagine it trying the other edges and seeing that they all cause cycles. For example, the next edge to try would be the edge DB, but that would cause a cycle. It doesn't add that. Another edge to try might be the edge BC, but that also causes a cycle. The edge BF also causes a cycle, and finally the edge AC also causes a cycle. So we have the spanning tree. And the claim is that this is a minimum spanning tree, but we would need to prove that. Okay, that's Kruskal's algorithm. I'll show you another algorithm using a very different approach, but also happens to be a greedy algorithm. And in the next segment, we will prove both these algorithms correct. The second algorithm is something called Prim's algorithm, which is another greedy algorithm for finding a minimum spanning tree. It uses a technique that will recur in other algorithms. And the technique is to think of the graph as divided into, the vertices of the graph as divided into 2 sets. So initially C is on one side and all the other vertices are on the other side, and now we're looking for the cheapest edge going across the 2. And you can see from C there are 3 options: an edge of weight 4, one of weight 6, and one of weight 7. So obviously 4 is the cheapest. This 4 is the cheapest. So Prim's algorithm is going to choose the edge CF. Now C and F are on the same side. C and F are together, and we're looking for the cheapest edge from them to the other side. And there are a number of options. There are a couple of 2s that we could choose. So let's say we choose the edge FG, let's say, as the edge that goes across. And now C, F, G are on one side. C, F, and G are on one side. And we want to find the cheapest edge from them to the other side. And again, there's a 2 that's available. That's FH or GH. So we chose GH in this case. And we continue in this manner. Now C, F, G, H are on one side. The other vertices are on the other side. And the cheapest edge joining both sides might be the edge of weight 4 from A to F, F to A. So we add that, continue, continue, and continue. So note that in this case, actually, Prim's algorithm produces a slightly different tree from Kruskal's algorithm. You might see a difference here at the bottom. These are both algorithms for the minimum spanning tree. How can they produce different trees? Well, they can do so only if both trees have the same cost. And you will see that if you add up the cost of the edges in the Prim tree and add up the cost of the edges in the Kruskal tree, you'll get the same answer. Actually, something stronger is true. If all the edges have different weights, no 2 edges have the same weight, then in fact, there's only one minimum spanning tree, and both Kruskal's algorithm and Prim's algorithm will find that very tree.